Hello. We are going to start talking about an introduction to gas laws. Okay, what essentially gas laws do is they mathematically describe how a gas would act under a certain condition. Now, one of the things we are looking for would be, for example, the pressure of a gas. What happens to the pressure of a gas when we change the conditions of the gas? So what are those conditions that we can change? We can change the temperature. We can change the volume of the container if we have something like a balloon or a movable piston. We can also change the number of particles, the moles. So there's a lot of things we can change. And what gas laws do, they help us to predict how those changes will affect, again, things like pressure and temperature. Okay? Now, essentially what this will do, this video will try to essentially give the PowerPoint version of what I did in class. All right? So, when we talk about gases, okay, we all hopefully know what a gas is. All right, we have solids, liquids, and gases. Now, there are two different types of gases. There are ideal gases, and there are real gases. When we look at these first gas laws, we are going to assume that these gases will behave ideally. Okay? Well, what does that actually mean? How does a gas behave ideally versus real? Well, we have to look at something called KMT, which is kinetic molecular theory. KMT is the basis for most gas laws and how the calculations and equations will all work. All right, and if you don't know anything about what units of pressure are, what units of temperature and volume, we will go through all that. And again, feel free to pause the video at any time to write these down, all these notes. Okay, so let's talk about the postulates that have to deal with KMT. There are 6 postulates, and we'll take them one at a time, and we'll discuss them and explain what makes an ideal gas behave ideally. Anyway, so postulate number 1. Gases are composed of large numbers of particles that behave like hard spherical objects in a state of constant and random motion. So gases are always in motion. They are not stuck in place like solids. Okay, they are constantly moving. And what happens is, due to this motion, they will put a force on the wall of its container. Okay, and that's where we get pressure from. Number 2, these particles will move in a straight line unless they collide with another particle or the walls of the container. All right, so if we can kind of look at these gas particles almost like billiard balls, they'll keep going in a straight line until they hit another particle or the wall of container. Boy, this is kind of hard to do it with my big fast fingers, but I'll do the best I can. Anyway, number 3, these particles are small, so the distance between these particles are pretty large. So the volume of a gas is theoretically mostly empty space. Which would happen, that means that these particles, they won't hit each other as much if they're smaller, and there's more empty space than gas particles. Number 4, there is no force between these gas particles or the particles of the walls of the container. Okay, and in a real gas, okay, there is a force between them, and that those forces are essentially gravity that do cause an attraction. All right. And number 5, the collision between gas particles or the collisions with the walls of the container are perfectly elastic. That means that no energy will be lost. So during the course of its life, as we study this gas in its perfectly ideal condition, we will not lose any energy. And that is important because if we did lose energy, these gas law equations, which you're going to soon learn 3 of them, would be more complex than what they are. And number 6, the average energy of a collection of gas particles depends upon the temperature and nothing else. So this is an important thing for an AP student to understand. Okay, that if we have 2 gases at the same temperature, they will have the same kinetic energy. Now, that doesn't mean they'll move at the same speed because, again, a gas with a larger molecular mass will move slower than a gas with a smaller molecular mass. So, for example, hydrogen gas, which is a diatomic molecule, has a molar mass of about 2.02 grams per mole, whereas carbon dioxide, CO2, is a gas at room temperature and is a much, much heavier molecule. It has a molar mass about 44.01 grams per mole. All right. So, if those 2 gases are at the same temperature, they will have the same kinetic energy. Right? But even though they're at the same kinetic energy, one gas will move slower than the other because kinetic energy, if we look at it, Ke, is 1/2 m, which is the mass of said gas, times its velocity squared. Okay? All right? So that's going to be more important a little later on when we talk about root mean speeds of a gas versus the real speed of a gas. Okay, so in this chapter we are going to assume that gases will behave ideally. Now they do not really exist, but it does make the math easier, and the approximation numbers will be pretty close to what they really are. Now when we come back in September, we will look on how to make corrections for gases that are real. All right, but over the summer we did not get to this. So anyway, we will assume that for right now, unless I indicate that the gas is real, all gases will follow kinetic molecular theory and therefore be ideal. All right, so let's talk about pressure. Okay, so these are the 4 things that essentially we're going to need to know about how a gas behaves. Number 1, again, like I just said, is pressure. Now, pressure is abbreviated or symbolized as an uppercase P. And pressure is essentially how much force that is put on the walls of the container of whatever vessel that you have this gas contained in. And we've all seen this in hopefully our lifetime, either blowing up a basketball, football, a bike tire, or even a car tire. Okay. Again, the less gas that's inside that container, or even a balloon, the less force is going to be put on it. All right. Now, we are Americans, so we tend to look at when we blow up something like a balloon or a car tire. All right, we look at things in PSI. Okay, PSI is a unit of pressure. It's called pounds per square inch. Now, in the AP chemistry world, okay, or any kind of science, is always done in the metric system. So pounds per square inch, not going to use. Old English, not happening. Okay? But what we will use, though, is ATMs, which is short for atmospheres. Okay? The atmosphere that we are in, the air, puts pressure on us right now. The closer you are to the ocean, like we are, all right, we essentially live a couple miles away. We're at sea level. So we get the most bang for the buck down here because we are closer to I would say, I guess, the average bottom of the container that is Earth. So our pressure is going to be at the most, where if you lived in a place like Denver, which is called the Mile High City, it is all the way up there, really high, so they experience less pressure. All right. We also can look at pressure in units of millimeters of mercury, okay, which I will discuss a little in the next couple of slides when we look at barometers. Analogous to millimeters of mercury is it a unit of pressure that you're going to see in AP that we call torr, which is short for torricelli. And another important unit is kPa, or kilopascals, and if you're just talking about a pascal, it is PA. All right, so those are essentially 1, 2, 3, 4, 5 units of pressure that we will see in our AP world. All right, so we talked about millimeters of mercury. Okay, a instrument to measure atmospheric pressures, okay, is something called a barometer. We used to have a barometer when I first started teaching, but barometers are filled with Hg, which is mercury, and mercury is not good to have around younger adults, or especially little children, because it interferes. It's a heavy metal. It interferes with the neurological development of children and younger adolescents. So we removed that from schools. So the average, if you're at the sea level, okay, we average around 760 millimeters of mercury. So if this column of mercury that is standing up is a meter high, okay, we can measure the force that the atmosphere, because this is open to the atmosphere, all right, so you have a big pool of mercury sitting right here in a vacuum tube, and we would measure how high that column is, okay. And if you read or listen and watch the news will talk about inches of mercury. I think today the pressure was about 30.08 inches of mercury, and it was rising, it was increasing, okay. And when the pressure increases, it also, a little side note here, it holds the water vapor in the atmosphere. So if you look at a barometer and that barometer is falling, okay, that means the atmosphere can do a less better job at holding that water vapor inside of a cloud, and hence it's going to rain out. Now, we call these 1, 2, 3 things, well, these units and these measurements, we call them standards. So you might hear the word STP, okay? S is for standard, and P would be for pressure, and obviously T would be for temperature. We'll talk about what standard temperature is in a second. But if you're at ATMs, standard pressure is 1 ATM, and standard pressure for millimeters of mercury or torr would be 760, and kilopascals would be 101.3 kPa. All right, so again, these are all equal to each other, so we can always use these identities to do conversions to. All right, and I will indicate what problems to do in the textbook to do those conversions. All right, so 4 things. We spent a lot of time here on pressure. Temperature, which we use capital T to indicate temperature, is always in K. K is a temperature scale, all right, called Kelvin. Now, we're used to, in America, we're used to using Fahrenheit, all right, but standard temperature is 273.15 Kelvin, or 0.00 degrees Celsius. Okay, and if you didn't know, at 0.00 degrees Celsius, water will freeze. And that's the whole Celsius scale is based upon the freezing and boiling point of water. So you always have to do work in Kelvin. Okay. Now, if you notice in Kelvin there is no degree sign, which in Celsius and Fahrenheit there is a degree sign, because there is no theoretical bottom or top to Celsius or Fahrenheit. But Kelvin, there is. There is a hard bottom. The coldest you can get is negative 273.15 degrees Celsius, or 0 Kelvin. All right. We call that absolute zero. Okay. So, anytime you need to convert between Kelvin and Celsius, you add 273 or subtract 273. So for example, all right, we use 25 degrees Celsius a lot. So in order to convert that, I would add 273.15. Now again, always remember your sig fig rules for adding and subtracting in the metrics, or in the metric system, or basically anytime you have a measured number, it's always least places behind a decimal. So you might say, well, 298.15, and we would drop the 0.15 off due to sig fig rules. Volume, when we talk about the ideal gas law, which is a law we're going to look at in a couple days or a little bit later down the road, will always be in liters, but for all the other gas laws we can use milliliters. Okay. Standard volume is 22.41. And the number of particles, or standard number of particles, is 1 mole. Okay. All right, and we're going to stop this right here. So the next video we'll be talking about the 3 gas laws, which are kind of introductory. And then once we get those 3 gas laws down, we'll get up to much harder gas laws, like combination and the ideal gas law. Okay, so reiterate, we need to know about pressure, temperature, volume, and number of particles, aka moles. Okay.